Okay, in this video we are going to look at my personal kind of tier list of the series convergence tests and kind of review what they say. And let's see. So I'm going to be ranking these literally just based on how I feel like ranking them. I mean, in each case, there's often a test that applies to a given series, so it's really hard to rank them overall. So it's kind of just how much I enjoy using them. But I will say some are more universally useful than others, and that plays into it as well. So I'm going to review what they say, and I'm going to tell you a little bit of how I think about them as I'm deciding if I should or should not be using them. We're going to look at some examples of series that I would use them on. I should also say I probably have a separate video about each of these tests at this point, and then there's videos of me going through the notes that I use in class, and there's a lot of other review stuff. So this is an overall approach to it, but you might want to dig in. I'll try to put links below to, some of the more detailed things about each individual test. So the ranks that I will be using are, I'm going to go from D, which is going to be the worst, but I'm putting that in quotes because, sometimes it's the test you need to use. And then we're going to go all the way up to the traditional, I guess, S rank, which would be the best or the most universally applicable or the one that I just enjoy using the most. So let's get started. So surprisingly, we're going to start with something that is unranked. So there's one thing that I guess is a test, but I don't really think of it as a test. I think of it more as like a big concept. And so that is the idea of the test of, just absolute convergence. So absolute convergence says the following. If the sum of the absolute value of a sub n converges, then the sum of a sub n without the absolute value converges absolutely. So this is like a quick way of dealing with a series that sometimes has positives, sometimes has negatives, or always alternates. It allows you to just look at it on a slightly easier frame. And so notice that absolute value right there. It's going to take it and turn it into a positive term series. And a lot of the tests that we have only work on positive terms, positive term series, I should say. So after we take the absolute value, you end up just using any of the tests that you know. I always think, to decide, why is absolute convergence a big deal? I'm sure there are a lot of reasons that I don't delve into because, honestly, I go up to, the convergence test, and then I don't really use these for things. I just show if a series converges or diverges in the material that I teach. But in my mind, one idea is kind of a little simple, I guess. It's basically easier for a series with positive and negative terms to converge because sometimes you're adding, sometimes subtracting, so it's not like you're universally adding to that sum. So if something is going positive, then negative, then positive, then negative, I think most people can agree that, that might converge. Whereas that idea of just constantly adding positive terms, it's like, how is that ever going to converge? Well, we know that it can. But if you only have positive terms and you still converge, then when you have positive and negative, it seems to me pretty clear that you would definitely converge. So that's how I think about it. So if you sometimes add, sometimes subtract, that's easier to converge than always adding. So if when always adding it converges, then it must converge when it is kind of alternating or sometimes positive, sometimes negative. So I have left this as unranked because it's really, it's an amazing concept. It's really useful. It does make a lot of problems easier to deal with, but I don't think of it as an actual test. I think of it more as a little loophole that we can sometimes use to make our lives easier. So with that said, let's move on to the actual rankings. So these are my D ranks. So these are the least useful or the ones that I dislike the most is probably the fairest way to say it. And number one on that list would have to be the direct comparison test, which I do not enjoy using. So here's what it says. Given that, so we have positive term series, so 0 less than or equal to a sub n less than or equal to b sub n for all n. If a sub n diverges, so a sub n, remember, is smaller than b sub n. So if a sub n diverges, then the sum of b sub n will diverge as well. On the other hand, if b sub n, the larger series, converges, then the smaller series, the sum of a sub n, must converge as well. All right, so that's what the direct comparison test says. I have ranked this here because I do not like to use it. It's a very useful test. It has its places. Any day of the week, I would rather use the limit comparison test. So this is why it has fallen where it's fallen. So let's look a little more closely at what it kind of says. So if the smaller series is diverging, the smaller series is going to kind of push the bigger series to diverge. That's how I think of that. Like, I don't know, like standing on the shoulders of giants type of situation. Like the little one is diverging, the bigger one has to diverge because it's bigger. And then on the other hand, if the bigger series is converging, I think of it as kind of trapping the smaller series. The smaller series has no choice but to also converge. So that's how I think about it. So one of the things that I dislike, there's so many things that I dislike about it. Most of them are that it's like not impossible, but like it's harder work to use this than it is to use some of the other series tests. You need to establish that A sub n is less than or equal to B sub n, which is annoying. And usually I just kind of assert that that's true. But you should actually be establishing it. One place if you're in BC, I guess would be the place Calc 2, Calc BC. If you're doing things with multiple choice questions, you're probably going to run into this. There's a lot of questions where they're like, which of the following would you use to show that blank converges by direct comparison or that blank diverges by direct comparison, right? So that's a case where you're going to need to know this. Or they'll give you basically the setup of the comparison test. They'll say like, A sub n is less than B sub n, the sum of B sub n converges, what do you know, that type of thing. So as I mentioned, I would always rather use the limit comparison test, and that obviously will show up in the list, farther down the road. But, this one exists. So what am I going to use it on? I mean, never if I have a choice, but if I am told the relationship between A sub n and B sub n and that B sub n converges, then I would obviously know that A sub n converges by direct comparison. That's one place. Also, I'm like kind of ignoring the fact that they have to be positive termed. Let's assume that they're positive termed for the purposes here. Something to watch out for, though, obviously, is the notion of cannot be determined, right? So if A sub n is less than or equal to B sub n and A sub n converges, there's nothing that we know, right? So we don't know if B sub n converges. We don't know if it diverges. It's just because A sub n is less than B sub n, we just don't know. So here's an example where you might run into like direct comparison is tricky. Like you have to know what you're doing, because if we want to direct compare something to 1 over 2 to the n, right, the sum of 1 over 2 to the n, which definitely converges, can we use it on 1 over 2 to the n plus 1, or can we use it on 1 over 2 to the n minus 1? So we have to decide which one of those is less than 1 over 2 to the n, because since 1 over 2 to the n converges, we can only use it to show that something smaller converges as well. We can't use it to show that something bigger converges or diverges. It's just not useful in that case. All right, so I would start off with this math. 2 to the n plus 1 is greater than or equal to 2 to the n. 1 over 2 to the n plus 1 is less than or equal 1 over 2 to the n. So the sum of, so the reason for that, by the way, is when you flip an inequality, when you take reciprocals within an inequality, you flip the sign. It's like the lesser known when do you flip the sign in an inequality. That's one of the places. So we have 2 to the n plus 1 is bigger than 2 to the n. Take reciprocals, therefore 1 over 2 to the n plus 1 is less than or smaller than 1 over 2 to the n. If you add up all their terms, then the left side will be less than the right side. The right side converges, so 1 over 2 to the n plus 1, the sum of, converges by direct comparison. So, I mean, that's a place that I would use it, but again, I don't want to use it, and I could have done the limit comparison test on that. So keep that in mind. All right, so we're on the D ranked things. I have another one that I'm going to put on the D rank. And again, this one actually, depending on how many series tests you use, could be controversial. I don't know. I don't think any of this is very controversial. The root test is my next D rank test. Basically, here's what it says, and then I'll explain why I'm ranking it here. We got let rho, the Greek letter rho, equal the limit as n approaches infinity of the nth root of the absolute value of a sub n, right? So again, it's absolute value. If rho is less than 1, the series converges. If rho is greater than 1, the series diverges. If rho is equal to 1, the test is inconclusive. Generally speaking, I don't like when a test can be inconclusive, but that has nothing to do with ranking it here because there's a lot of tests for which that happens. So here's what I am ranking this based on. It does have the absolute value, so it can do absolute convergence. That's good. But I never want to use this test. I don't know why. There's not really a compelling reason, except taking the limit of the nth root of something is, in my mind, just like it doesn't come to my head. Like I just don't think to do it. So the next reason is that I forget about it like a lot. I will flounder around with other tests and then finally realize like, oh, I'm supposed to just use the root test on this, and it'll make it work in 1 second. So when you think, it's not like a bad test. Don't get me wrong. The way I'm ranking these is purely just how I feel about them. And I think how common they are, maybe. But that, whatever. The other thing is I teach, mostly AP calculus, and the root test is not on the AP exams. It is not a part of the curriculum. Things could change. I don't really know why it's not a part of the curriculum, other than limits of nth roots tend to be a little more involved, I guess, when they're involved. Otherwise, they're just like super straightforward. So things could change, might be on it at some point. And let me tell you, I have had students in the past who would rank this the highest test. They love using it. So they might give it like an SS or an S plus ranking. This is all subjective. But I don't like using it. I don't remember to use it frequently, partly because I get in that AP calculus frame of mind and I'm just like, go. But anyway, let's see what's good about it. I mean, it's a good test. It's got a lot going for it. Also, it's like, I think more, I read like an article or a PDF at some point. It's like more universally applicable than some other tests. So it does have a lot going for it. I just, don't like it. All right, so since you're taking the nth root of something, this will work really well if a sub n has an nth power. So what do I mean by that? Well, something like the sum of 1 over 3n plus 2 to the n, right? Immediately you take the nth root, you just get 1 over 3 to the n plus 2, and then that limit is obviously 0, which is in fact less than 1, and so it will converge. That's a kind of a fine point. 0 is less than 1. Don't forget that. I don't know why, but when people are doing series tests, they often think like 0 is a bad thing to get. It's not necessarily a bad thing to get, right? And it's definitely less than 1. So this series that we're looking at here would definitely converge because that limit of the nth root is 0, which is less than 1. So that would converge. And do you see how fast that was, right? I would not think to use the root test on that typically, but it's super fast. Or you could have something like this, right? The sum of 2n plus 3 over 5n minus 4 to the 2n. So if I take the nth root, it's just that quantity squared. If I take the limit as n goes to infinity of that, I just get 2/5 squared, which is 4/25, which is less than 1. So this converges. Very fast test, but I never think to use it. I would try to do the ratio test on this probably, and I would just be like, ugh, this limit is terrible. So yeah, watch out for it. Think to use it. But I'm still ranking it D rank because I don't like using it. I don't think to use it, and it's not on the AP exams. However, it is a test for absolute convergence, which is a big thing. And the other thing is, and I fall into this all the time, you should definitely consider using the root test when the ratio test feels like you're just doing so much work. I always dive in and try to use the ratio test, and you'll see in the rankings where that's going to show up. You probably guess if you know me at all. But when the ratio test seems to be failing you, think about the root test. And also, it has the exact same convergence, divergence, inconclusive statements, conclusions as the ratio test. So like you don't have to memorize an entirely new thing. You just have to remember it exists, which is the problem that I typically have. All right, moving on. Now we're going to get to my C ranks. So these aren't, again, none of them are bad. None of them are like great, whatever. This is all personal choice. My first choice for a C rank, I think though within the rankings, like the C rank, I am kind of ranking them from worst to best in my opinion. So there is like an order. I mean, there's an order implied anyway, but like within each ranking, there's also an order implied. So telescoping series, going to be my first C rank. So here's a telescoping series. The series, the sum of a sub n, is telescoping if all but finitely many terms remain after cancellation. So why would I put this at C rank? Well, it's not on the AP exam, so I don't know why. It could totally be on the AP exam, and I bet someday it will be, because you tend to do like partial fractions on these. I'll talk about that in a second. But it's also really annoying to define or recognize or state what a telescoping series is. It's very easy to do it, and you like look at them and you immediately see, once it's in its proper form, you'll see that it telescopes right away. But it's not easy to just like make a statement about it. And so, and any series that is telescoping, you can tell if it converges or diverges more easily with other tests. So, there's that. It does have one huge advantage over some of the other things, though, and that is that you can actually find the sum. If you have a convergent, I guess all telescoping series converge by definition. So when you recognize that you have a telescoping series, you can find the sum, which is unusual. You can't do that for most of the series that we look at. We just know that the sum does exist. We don't necessarily know what it is. And then we'll talk, later in life, you'll talk about the error involved, so you can, know how close you are to this, whatever. There's a lot going on with finding the sum. Mostly we're concerned with, does it converge or diverge? This type, you can find the sum. The other thing is it often shows up if a series looks like, if a sub n looks like you could do partial fractions on it, then it's probably, or at least possibly, a telescoping series, which is why I think they could be at some point added to the AP curriculum, because partial fractions is something that you do, at least in Calc BC. So, I wouldn't be surprised if in the future it does show up. So these are things, they look like partial fractions. You do the partial fractions, then you see if it telescopes. And then this is the reason that this is ranked so low for me, C rank, is if you don't need the sum, the limit comparison test, usually to a P series, is just going to tell you that you converge or diverge. You don't go through the process, right? It's a type of series. I don't even know if it's really a series test. I always include it as a series test because, I don't know. Like, why did I unrank absolute convergence and I'm ranking this? Who knows? But choices have been made. So let's look at some. The first one would be this. So I've already kind of done the work so that you can see, like, imagine combining that into a common denominator and then expanding it. That would look like something you would do partial fractions on, right? That's how you kind of know that you might have a telescoping series, but they don't need to telescope just because you can do partial fractions. So that's annoying. Like, for it to be partial fractions, you need to have a minus sign in between. Otherwise, you're just going to keep adding stuff forever, so it's never going to telescope. It's never going to, like, collapse down to just the first and the last term and then kind of take the limit. So looking at this, you get a sense of what telescoping really means, though. So if we start writing out the terms, right, n is equal to 1, we get 1 minus 1/2. 2, we get 1/2 minus 1/3. And then 1/3 minus 1/4. And then we're just going to, like, keep going forever, right? So the telescoping is how that minus 1/2 plus 1/2 cancels. And then minus 1/3 plus 1/3 cancels. And then we know we have a minus 1/4, and the next will be plus 1/4. That's what the telescoping is. And ultimately, the only term that will be left after you take the limit as n goes to infinity is just that first term. It's just 1. We can find the sum of this thing. So that's pretty neat, because not every test allows for that. So, it's cool, but it's really specific and not that common, and you have to do partial fractions most of the time. So, for example, you might get something like this. 2 over n squared plus 4n plus 3. This looks like something you'd use partial fractions on. I'm not actually going to do it, but if you did do partial fractions on this actually is a convergent series. But again, if you know the limit comparison test, you just compare this to 1 over n squared. 1 over n squared converges, this converges, blah, blah, blah. But not everything that looks like you could use partial fractions on it will result in a telescoping series, and not all of them will converge. So just be on the lookout for that. That's why I've given this a C ranking. All right. The next test that I am giving a C ranking to. And remember, C rank, it's not terrible. It's like it's an average type of thing. The integral test. All right, so why would I give the integral test this? Let's see what the integral test says. Given the sum of a sub n and f of x such that f of n equals a sub n. So f of x is kind of generating the terms of the sequence that you're adding up to get the series, where f of x is positive, continuous, and decreasing if the integral from a to infinity of f of x dx converges, then the sum from 0 to infinity of a sub n converges as well. So notice I'm just starting at a there because it just needs to be true eventually. And so it's the improper integral converges, the series converges. If the improper integral diverges, the series diverges. They just do the same thing, which is how I remember it. So I am ranking this based on the amount of work that it is to pull off this test. So there's just so many things. Like, can you integrate f of x? Remember, integrals are a little harder than derivatives, right? Like, you can't just integrate everything. So you got to be able to integrate the thing. You probably got to show that the thing is positive, continuous, and decreasing. All of that's kind of a pain in the neck. And then you got to do an improper integral. There's like a lot of work involved, and it's very notational. It's a lot. So if you can use a calculator, on the other hand, this test is fantastic because a calculator will do all of the work, and you just have to look at the results and be like, yes, this converges, or this diverges. So definitely this one, technology will benefit you quite a bit. So notice we're starting with A. I mentioned this before. You don't actually have to have f of x be positive, continuous, and decreasing like forever. It just needs to eventually be positive, continuous, and decreasing, right? If it starts at 25 and 25 to infinity that happens, then if that improper integral converges, the series will converge because the first 25 or 24 terms of your series are a finite number. So if from 25 to infinity you get a finite number, just add them together. So it doesn't need to start necessarily at the same value that the series starts at. So watch out for that. And then it's just a lot of work, right? We need positive. How do we show something's positive? We show that f of x is greater than 0. We might have to do the math on that, right? Usually I'll just state that this is true. We have to show something's continuous. How do we show it's continuous? You notice that there are no discontinuities. It's always hard to show that something's continuous over like a... it's easier to show something's discontinuous than to show that it's continuous, right? So is it continuous? Well, does it have discontinuities? If the answer to that's no, then it is continuous, right? I don't know. I don't really like showing that either. And then decreasing. Decreasing is like the classic of Calc 1. We're going to have to find f prime and show that it's less than 0. So it's a lot of work. Like, just that's a lot of work. Then you have to do the improper integral. So when would I use this? I would use this if you're required to use it, which on the AP exam, sometimes you are, like free response questions, they're just like, use the integral test. Usually, however, in like part A of that, they'll say like, show that the function is decreasing on whatever. You already will, like, it'll be a positive thing. Like, there's no negatives anywhere, so you know that it's positive. And then continuous, like, you'll know that there are no zeros in the denominator or like weird jumps or anything. So you will have already set it up, and then they'll ask you to use the integral test. So if they tell you to, the other time I will use the integral test or consider using the integral test is when I look at a sub n, and I think that looks like a function that I could just integrate. And if that's the case, sometimes I'll do it because I like reviewing integrals and like, taking an integral every once in a while. But that's when I'm thinking integral test for sure. When you're doing the integral test, though, you're doing an improper integral. So you got to remember the notation, right? So the integral from a to infinity of f of x dx, you have to use the proper notation. Will be the limit as b approaches infinity of the integral from a to b of f of x dx. So don't lose points by using improper notation on your improper integrals. So that's a thing I should say more. Improper integrals require proper notation. All right, so like, what do they look like? I mean, anything you think you could integrate. But so this, a lot of things like this, where it looks like I just have to reverse use of the chain rule, right? Like let u equal. First, I'd rewrite this thing as e to the negative n cubed, and then let like u equal negative n cubed and go from there. Like, we can integrate that. So that's one that I would definitely consider use. And also, what else am I going to use on this? I don't want to try to direct compare it. I have no idea what I'd limit compare it to. At this point, I'm thinking like I basically have to use the integral test. Other things like this, you can definitely show that this one is going to converge or diverge. I think this diverges. This diverges. You can show that this diverges in other ways, like direct comparison to 1 over n, for example. This is an example where I would use direct comparison potentially, but you can integrate that. Let u equal natural log of n, and just integrate. So these are places you would potentially do it. And as I mentioned, on the AP FRQs, they will sometimes set you up so that you basically have to use it, or they'll literally tell you that you have to use it, in which case, you just kind of go for it. Okay, I'm actually this doesn't impact the video. I'm gonna take a break so that I can drink some water. I will be back in a second to continue. We're still in the C ranks, but I'll be back in a second. Okay, I'm back. We're continuing our C rankings here. And so the next up is the nth term test for divergence, which I think you can make a case should be a lot higher. Some people might make a case should be a lot lower, and I have decided to put it here in the C ranking. So let's take a look at what it says. It basically says if the limit as n approaches infinity of a sub n is not equal to 0, then the sum of a sub n diverges. That's it. So I'm ranking it here mostly because it can't actually tell you if something converges. I've seen so many students incorrectly use this over the years that it's, definitely kind of colored my opinion on this. So yeah, this can only tell you if something diverges. It can never tell you if it converges. Also, I'm looking at this. I feel like I used the wrong color to highlight converges there, but or I use I don't really know. Whatever, it's fine. All right, so this is a great test for divergence. If you take the limit and you don't get 0, then you know something diverges. Perfect. On the other hand, it can't tell you if anything converges, which is bad. You should definitely consider using it for every series. I almost never use it. It will save you a lot of time if something obviously diverges. I've spent hours of my life, if you add it all up, trying to show that something converges or not being sure if it converges or diverges, when at the end I look at it, I'm just like, oh, if I just took the limit to infinity, I would not get 0, so it must actually diverge. So it's definitely one to always think about. I don't use it that much, to be honest. I probably should. But since it can't tell you if something converges and can only tell you if it diverges, I only use it if I really suspect something diverges and it looks like the limit will be easy to take. I don't know if that's laziness or a good strategy, whatever. So you might need to use L'Hopital's rule to actually find the limit, which is another thing. And then you just have to watch out. So it's always good to know the counterexample or the thing that will tell you definitively the thing I think about this test is not true. And the one for this is definitely just 1 over n, the harmonic series, right? So the limit as n approaches infinity of 1 over n is definitely 0, but the harmonic series famously is divergent, right? So this is a divergent series. So if the limit is 0, you don't know anything. If the limit is not 0, you definitely know the series diverges. You got to keep these things in mind. So some examples, I don't know. You could use it on literally every series, and it will tell you that a series diverges if it does, and if you can find the limit, but it will never tell you if a series converges. So so maybe on this is the limit as n approaches infinity of this is famously equal to e, which is definitely not 0, so that series diverges. If we're just doing 3/5, so not 3/5 to the n, just 3/5. 3/5, the limit as n approaches infinity is 3/5, which is definitely not 0, so that would diverge. So it's a good test for divergence. It is a useless test for convergence, and so that is why I've given it a C ranking. All right, next up, we're going to talk about my B ranks. So we're getting up there. We're getting to the ones that I like using, that I think are the most useful, etc. The first one is the alternating series test. So let's see. The alternating series test says, given the series, so it needs to alternate, right? -1 to the n times a sub n, or -1 to the n plus 1 times a sub n. So it's got to go positive, negative, or negative, positive, negative, positive. It can't do weird things like plus, plus, minus, minus, or sometimes plus, sometimes minus. It's got to actually alternate back and forth. The series converges if the series alternates, which it must if it looks like that, if a sub n is decreasing. So if a sub n plus 1 is less than a sub n, and if the limit as n approaches infinity of a sub n is 0. So you gotta have this. It's gotta be alternating. And also notice the way this is kind of like formulated, it's the way they're written like in textbooks, it's usually that a sub n by itself is positive, and then you're multiplying a sub n by like this alternating factor, like -1 to the n or -1 to the n plus 1. I always think that's just curious, because like you could have just slapped an absolute value around like the whole term and it would have been like easier to deal with, but then I guess it's harder to convey. I don't know, whatever. So I have ranked this here because I like it more than what I've done already, and I like it less than what we're going to do later. Also, it's really specific. It only works on alternating series, right? So that's good, though, because it will deal with something that's sometimes positive, sometimes negative. Some of the tests only work on positive term series, and then if they don't converge, absolutely, like, what are you going to do? But that's okay. So if you're using this in AP calculus, I'm sure that in like some more advanced calculus or like real analysis classes or whatever, you probably run into things where this isn't the case. But in AP, if an alternating series is going to diverge, then the limit as n approaches infinity of a sub n will not be 0. So that's where the nth term test is really helping you. So if you're using the alternating series test, you are saying that something converges, and that's okay. So it's popular. It comes up a lot. And I would say especially when you're dealing with Taylor series, Taylor polynomials, Maclaurin series, when they tell you to substitute in a value of x, it is extremely common that you will get an alternating series when you do that, and you can use this to show that that series converges. In terms of like the requirements, I usually just say that they're true. So I'll just assert that the terms decrease in magnitude to 0. So I'll say like, the series alternates, has terms that decrease in magnitude to 0, which is covering like decreasing, and it's covering the limit is 0. And I stated that it alternates, so I'm like showing all the requirements. I've never really run into a problem, especially on the AP exam, where I had to like prove any of those facts. But if you did, they would probably run you through that in like part A of the question, like show that this function is decreasing. And then in part B, it'd be like, oh, that function is actually a sub n for this alternating series. So you would have done the work already. The most famous alternating series is the alternating harmonic. Also, that should start at 1, not at 0. Like, how are you going to start at 0 when you have to plug in? So whatever. You could change that. I'm not going to. And then you can often avoid doing it at all. Not on this one, because if you take the absolute value, you get 1 over n, and 1 over n diverges. So this is not absolutely convergent. It's just conditionally convergent. But you can usually or often avoid it by just looking for absolute convergence, by taking the absolute value of the nth term and seeing if that converges. But the alternating series test is huge, really important. I mean, like from an AP perspective, I would say this is maybe like the second most important test. But in like overall, I'm not ranking it that high because I don't like it that much. So here are some things that I'd use it on. I mean, basically anything that alternates, right? We got -1 to the n and then a thing, or -1 to the n and then another thing. That's when you're gonna think to use it. Remember, if a series converges when it alternates, but not when it does not alternate, then the series is called conditionally convergent. That is a topic that's on the AP exam, but literally just that's the question. Like, is this conditionally convergent, meaning it converges when it alternates, or is it absolutely convergent, meaning it converges when you take the absolute value? So it's a thing. All right. Moving on, we are now at the A rank, right? So we're getting way up there. So these are going to be, also, I don't know if you noticed, but literally the only B ranked series test that I have is the alternating series test. It's like the dividing line between like the great ones and the ones that I just don't really want to use. But it's utilitarian. You're going to use the alternating series test a lot. So our A rank series, here we go. These are the ones super common, super useful. Also very easy to use or identify. So the first one is P-series. Is P-series really a series test? Is it any more a series test than telescoping series? I don't know. But P-series are the sum of 1 over n to the p. If p is greater than 1, the series converges. If p is less than or equal to 1, the series diverges. what is not to like about this, right? P-series are extremely common, right? So you're going to run into them all of the time. They are very useful in making comparisons to other series. So like if you are doing direct comparison, you might be direct comparing to a P-series. If you're using limit comparison, you're almost certainly going to compare it to a P-series. So they're very useful in that regard. And then like, just look at them. They're so easy to identify and to determine convergence or divergence. I mean, like, it's fantastic. So P-series, my first A rank, I mean, it almost is S rank because, like, who doesn't want to run into it? But it's not, again, not, is it really a series test? I don't know. Or just a type of series. Whatever, we get to decide. So where does this come from? It's literally just a generalization of the integral test. If you didn't know that P-series existed, you could use the integral test on every single one of them and get the result you need every single time. But like make the generalization, right? I don't even really have a lot to say about this. Like, it's a fantastic test, but like it's so straightforward that there's like not much to really say about it. We already said that we use it in the comparison tests like all the time. And it's also like absolute convergence. You often end up with a P-series, especially like alternating series. So say you have something like maybe -1 to the n, 1 over n to the fourth, right? Take the absolute value of that and you just get 1 over n to the fourth. That's a P-series. P is equal to 4, greater than 1, converges. So the whole thing converges absolutely. Like, these will come up often, and so you got to know them, but they're fantastic. So I would hope that any series is going to be a P-series. We don't really know how to find the sum of them, which is kind of a detractor, right? So I don't know. It's good stuff though. So here are some examples. I mean, I don't know what really you'd want to see. 1 over n to the 8th, 7th. These are tiny. 1 over n to the 7th. So P is equal to 7. That's greater than 1. It converges. There you go. It could look like this, right? So it's important that it's 1 over n to the P, where technically P has to be greater than 0. So otherwise you're not really, like, just rewrite it. It's got to be in the denominator. So I'm going to rewrite this. 1 over n to the 8th. 8 is greater than 1, so this thing converges. Yay. Sometimes you get radicals involved, like 1 over the 5th root of n. Rewrite that with rational exponents, so we get 1 over n to the 1/5. 1/5 is less than 1, so this thing diverges. That's P-series for you. Definitely an A-ranked series test. I would love to run into P-series all the time if I could. The next of the A ranks is, I think, like the companion series to this, and that's geometric series. Geometric, I don't know, like, it's still, to me, it's not S rank, but like it probably should be. And again, there's a lot of emotion involved in ranking these things, obviously, right? So given either a times r to the n or a times r to the n minus 1, doesn't really matter. I'm just showing you the two like textbook definitions that you'll see. If the absolute value of r is less than 1, the series converges. If the absolute value of r is greater than or equal to 1, the series diverges. That's it. That's fantastic again. So what am I ranking this based on? Geometric series are really common. I would argue that for certainly the things that we do in my courses, they're much more useful than P-series. Like, P-series are a fact. Geometric series are like a tool that we work with all the time. We're rewriting functions as geometric series as functions, partly because we can find the sum of them. So super common, super useful. I would say that they're like quote unquote easy to work with once you get the hang of it. You can play around with them a lot. Like they're pretty fun. And you know, I like to use them. And I often hope that something's geometric. I get a little excited when I see like, it's geometric, yes. So something to know. All convergent geometric series are absolutely convergent because you're looking at the absolute value of R. So you're always looking at a positive term series, regardless of, if it started out alternating or not. We can definitely find the sum, which is a very big deal, and we use that fact a lot. And you notice with most of the tests, we can't find the sum. We just know it does exist. So the sum, I always say, is the first term over 1 minus the ratio. That avoids the scenario where you're summing from n equals 50 to infinity and you just memorized a sub 0. No, it's the first term. Whatever you get when you plug in that initial index is your first term over 1 minus the ratio. There you go. Make sure the absolute value of r is less than 1, though, right? This thing will claim to give you a sum for the series, regardless of what r is. You have to know if it should be finite or not. I would say it's definitely, with p-series, the next most common type that you're going to compare things to. So in that regard, it kind of like helps the direct comparison, limit comparison tests, do their jobs. So you got to know all about these. Geometric and p-series are like, they're the I don't know, the basis upon which a lot of other tests kind of like operate. So if you do need to, you can find the ratio by dividing consecutive terms. So this is if you are given the terms like all written out, and you have to decide if it's geometric or whatever. So for example, if you have like 6 minus 3 plus 3 halves minus 9 fourths plus blah, blah, blah. So what you're going to do is you're just going to do negative 3 divided by 6, right? So it's like the next term divided by the previous term. So negative 3 divided by 6 gives you negative 1 half. And then check another one, right? So 3 halves divided by negative 3 will give you, again, negative 1 half. You're getting the same ratio every time. That means r is negative 1 half. The absolute value of r is less than 1. This thing converges. Another thing to watch out for is, I don't really know why. So like this example uses the series e over pi to the n. E is like 2.718, pi is 3.14. Pi is bigger than e. Keep that in mind, because a really common ratio that they like to give is e over pi or pi over e. You've got to know like what's going on there. You could also, it's really common to kind of like have a lot of things raised to the nth power. When that's the case, what I like to do is kind of collect, in quotes, everything to the n. So what I mean by that is you have negative 1 to the n, 3 to the n, 5 to the n. So really you have negative 1 times 3 over 5 all to the n. So I will rewrite this like this. R is negative 3/5. Absolute value of that's less than 1. This converges. So that's how I kind of deal with that. And those are our A rank things. So the A ranks were P-series and geometric series. And that is it. I mean, there aren't a lot of series tests, so like, you got to choose how to distribute them. Next up, finally, are S ranks. So these are the ones that I find myself using all the time. I kind of enjoy using them. They're very powerful. They work on a lot of things. They're maybe easier to use, maybe not. But I just think of them as like, these are my go-to tests. The A ranks, P-series and geometric, are like I can identify it and know what's happening. These are the ones where you have to do the work. But sometimes you still look at it and know the answer. You just, have to do work. So first up, limit comparison test. The limit comparison test says a lot. Given the series sum of a sub n, sum of b sub n, a is greater than 0, b is greater than or equal to 0. Oh wait, that's wrong. A is greater than 0. B has to be greater than. I got a mistake here. You can't divide by 0, so b has to be greater than 0. Like you can't divide by 0. So let's say a is greater than or equal to 0, and b is just greater than 0. It's not really going to impact anything, but like for the purposes of being correct, I should have done a is greater than or equal to 0. B is greater than 0, because we do want to avoid dividing by 0. I even wrote to avoid dividing by 0 and then did it wrong. If the limit as n approaches infinity of a sub n over b sub n is equal to L, where L is positive, which it will be because the terms are all positive, so I've never really understood that part. Positive and finite. Oh, I guess it has to be positive because it can't be, it's not non-negative. Like you can't get 0 as your answer. You have to get a positive. Positive and finite. So you can't get 0, you can't get infinity. Then both series do the same thing. They either both converge or they both diverge. So if L is positive and finite and B sub n converges, then A sub n converges. If L is positive and finite and B sub n diverges, then A sub n diverges. They do the exact same thing. So you do need to know, I always think like you're given A sub n, you come up with B sub n. You need to know what B sub n does. Fortunately, you're going to be using like P-series or geometric series for the most part as your B sub n. And, we just talked about them. You know what those are doing. So you don't have to wonder, like, does it converge or diverge? Sometimes you have to do more work, though. Sometimes you got to do the integral test on a thing to begin with to get the series that you're then going to limit compare. But that's okay. So what is this ranking based on? It's amazing. This is an amazing test. I use it all the time. I use it instead of direct comparison every chance I get, unless I'm forced to use direct comparison. It's kind of like my go-to, after the other S rank tests. This is what I'm looking to use. Also, so here's how I think of it. This allows you to figure out if something converges or diverges based on just what the series kind of looks like. I'll look at a series and be like, that just looks like 1 over n cubed. 1 over n cubed converges. This does too. And then if somebody's like, how do you know? I'll be like, the limit comparison test. I just didn't do the work. So, for example, this thing, right? We got 3n squared plus 5n over 6n to the fourth minus 3n cubed. Well, if you've done enough stuff involving infinity, you know that basically you ignore everything except the highest powers in the numerator and denominator, the most powerful thing. So really in this case, I'm just going to compare this to, like, in the numerator, I see n squared, and in the denominator, I see n to the fourth. So I'm going to compare this to n squared over n to the fourth, which is just 1 over n squared. 1 over n squared converges, so the given series converges. It's amazing. It, like, really lets you look at a series and be like, that thing just looks like a convergent geometric series, so it converges. This looks like a convergent p-series, it converges. It looks like a divergent p-series, so it will diverge. It's the test that allows you to actually, like, formalize that it looks like. This won't work, however, on an alternating series. You have to have positive term series, so that's a disadvantage. But maybe your alternating series is absolutely convergent, in which case you can reintroduce the concept of using this. So that's kind of useful. The other thing, I think the thing that people initially struggle with is you do have to know what the series you're comparing it to does, right? But we just talked about it. Like, you can either use any of the other tests to determine that the series converges or diverges, or it probably just is a p-series or geometric, in which case you know going in what's happening. And then I will, like, every time use this instead of direct comparison. Like, as soon as I learned this, back when I was learning calculus, I was like, I'm never direct comparing anything again. I'm sure that there are scenarios where you have to use direct comparison. We just don't run into them all that much. But I limit comparison for life. If I had to choose, this is it. And you can tell because I put it in the S rank, right? This is one of the top 2 for me, for sure. All right. The next test is the ratio test. If you were in my class and you went through my notes, or you just went through my notes, you know that I think the ratio test is the best test ever. I love using it. I think I just like doing a lot of algebra, and so it appeals to me. But here's what it says. Given the sum of a sub n, we're going to let rho, again, so ratio test is related to the root test. They're very close siblings. We're going to let rho equal the limit as n approaches infinity of a sub n plus 1 over a sub n. Let me just take a second and say, that could also have been the limit as n approaches infinity of a sub n over a sub n minus 1, or like a sub n plus 3 over a sub n plus 2. It's just got to be consecutive terms, but the bigger one goes on top. So, and if you remember how we found the ratio for geometric, ratio test feels a lot like the geometric series test. So it's like it took that concept and just like made it bigger. But here's what it says. If rho is less than 1, the series converges. If rho is greater than 1, the series diverges. If rho is equal to 1, the test is inconclusive. And then you just have to use another test. But this is the best test by far, I think. I love to use it. I like simplifying all of the algebra involved. I like taking the limit. I don't know. So we get to do the algebra. It's also like extremely useful, very common, especially when you move beyond series of constants and you move into like power series. You're going to find yourself using the ratio test a lot. It's not really what this video is about, but the ratio test really shines as you kind of like move forward. I definitely like it better than the root test. And also, this is an underrated thing. You don't need a lot of intuition to use the ratio test. You just have to be willing to do the algebra. And then the result is just going to like drop out. And you're like, okay, so this thing converges. And I think that's good because when you're first doing series stuff, it feels like you have to already know the answer going into the problem, which in a lot of cases kind of is true, I guess. But the ratio test takes that out a little bit. So it's more of a like, it's good for workers. People who like to work hard, ratio test, and I love working hard, so it's good for me. It works on all kinds of series, but in particular, I would consider using the ratio test if there's a factorial anywhere in the problem. So if you see an n factorial, an n minus 1, any type of factorial in a problem, I'm immediately thinking I should probably use the ratio test on this thing. But I'll also try to use it on all kinds of stuff. It is a test for absolute convergence. Notice the absolute values. So it's a limit as n approaches infinity, the absolute value of a sub n plus 1 over a sub n. So it does test for absolute convergence, which is amazing. As I mentioned, once you start doing like power series, you're going to use this test to find the interval of convergence. Excuse me, which again, it doesn't matter if you don't know what that is right now. If you're only at the point where you're really reviewing the series tests, that's fine. But later in life, man, ratio tests, you're going to be using it all the time. And then a lot of technology can deal with this, right? If you have a computer algebra system, a CAS, like Wolfram Alpha, TI Inspire CAS, whatever, it can do the limit for you so that like it takes that work out of it for you. Ratio test, just fantastic. I don't know. So much to say. Like, do I even have examples? Not really, because I will try to use the ratio test on anything. Throw anything at me, and I'm probably going to initially think like I could probably ratio test it. I usually think, should I ratio test this? And if the answer is no, then I move down the tiers and start thinking like, well, what else am I going to do? But let me just leave one caveat for the ratio test for sure is it will never, ever, ever work on a P-series or anything that looks like a P-series. The reason for that is that you will always get 100% of the time, a P-series or something that looks like a P-series is going to give you 1 when you try to do the ratio test on it. So for those, but we already know you should be using the other S-ranked series test. You should be using the limit comparison test on those. But the ratio test is fantastic. It's the way to go. All right, so just to kind of summarize for you how I ranked all these things. My S ranks were the limit comparison test and the ratio test. Fantastic. I love those two tests. Moving down to A rank, we had P series and geometric series. Again, like, could they have been S rank? Like, probably, but I think the S rank series are a little more powerful and more generalized and whatever, but definitely those are A rank. For B rank, I had the alternating series test. I think of that as the dividing line between like the series tests I really want to use and the series tests that exist and sometimes I have to use. C rank, I had telescoping, integral test, and the end-term test for divergence, which was really only there because it can only tell you divergence. It can't tell you anything about convergence. For D rank, I had the ones that I just don't want to use, the direct comparison test and the root test. And then the unranked, I went with the test of absolute convergence because, I don't know, that's like you throw absolute value around it and then use any of the other tests. So like, how am I going to rank that? So I just left that off. But anyway, that's, I think, kind of a fun way to run through these and review them. That's my ranking. Curious if you have your own ranking, how you feel about it. I hope you found this helpful, and good luck.